students, we are studying direct approach based load flow analysis, and till now whatever distribution load flow analysis method we have seen they are applicable only for radial distribution systems. So, whether it is backward forward based algorithm or direct approach based algorithm, we have used them for radial distribution system. However, as I told you in the last class, there are some cases where distribution system is operated in weakly meshed mode. In that case, whatever algorithm we have studied, they are not applicable. Basically, this direct approach based method we should be suitably modified so that we can use it for weakly meshed system. So, in this particular lecture, we will see how we can use this direct approach based method for weakly meshed distribution system, because you can modify this BIBC matrix and BCB matrix such that it can be used for weakly meshed system. Now, let us see how we can use this method for weakly meshed system. So, in case of weakly meshed system, let us consider a simple system which we are already considered. So, let us say you are having this branch 1, branch 2 and then your branch 3. So, this is node number 1, 2, 3, 4 and let us say one more, there is 5, and we have considered this system where there is one more node which is say node number 6 here. Then this current we called as I12, this current I23, this is I34, this is I45, I36, and at each node there is load current I5, I4, here there will be I6, here I3 and then say your I2, and we have seen how to solve load flow problem for this one. Now, let us consider you are having weakly meshed system. Let us consider one weakly meshed system where let us say this and this node is connected such that there is one loop which is getting formed here, and when you connected this node 5 and node 6. So, in this particular branch there will be current which say I5 6 is flowing in given shown direction. So, here if you write your KCL equations, let us say if you are applying KCL at node number 5, then I can write your I45 will be equal to your current I5 plus I56. So, when I am applying at node 5, when I am applying KCL at node number 4, so it will be I34 current which is approaching towards node will be equal to your current I4 plus I45, and I4 we already got it here which is basically I5. So, I45 is actually I5 plus I56, and then let us apply KCL at node number we will first apply to the say loads node number 6. So, it will be I36 which will be equal to I6, and since direction of this current which is I56 which is minus, so it will be I56 here, minus I56. Then apply at node 3. So, I23 will be equal to I3 which is load current at node number 3 plus I34 which is going out plus I36 which is also going out. So, if you add them it will be I3, I36 we already got it here. So, it will be I34 first I will write. So, I34 is plus I4 plus I5 plus I56, and here it is plus I6 and minus I56. So, this will get cancelled out. What will remain is I3 plus I4 plus I5 plus your I6. Similarly, in I12, we can get the KCL at node number 2. So, I12 will be equal to I2 plus your I23, which will be equal to your I2 plus I3 plus I4 plus I5 plus I6. All the currents are coming. Now, you got here various equations. Let us say this is equation number 1, this is equation number 2, this is equation number 3, this is 4, and this is say 5. Now, one more equation I am adding, and in that equation I am saying current I56 is actually equal to current I56, and this I am saying equation number 6. Now, if you write these equations into matrix form, on left hand side matrix you will be having these currents, basically all the branch currents. So, from equation number 1 we are on the left hand side I12, equation number 2 we are having I23, equation number 3 we are having I34, equation 4 I45, equation 5 I36, and equation number 6 we are having I56, which is equal to some matrix say here, and the currents which are involved here are basically I2, I3, I4, I5, I6, and one more current which you are having is I56. And after knowing this equation, I can easily write the matrix, which is, so from equation number 1 you can see we are having all the currents except I56. So, here there will be one entry everywhere except I56, because in equation number 1 we are not having I56 current. Equation number 2 we are not having I2 current and I56. So, there will get 0, otherwise all the currents are present in equation number 2, and this is also 0. And if you see the equation number 3, which is basically this, here I2, I3 are not there, and so you are having I2 is not there, I3 is not there, I5 is there, I4 is there, I5 is there, and I56 is there. So, here we are having 0, and then here we are having 1. I6 is not there in that equation. So, if you see equation number 4 here, I45 is having only 2 terms, which is I5 and I56. So, here I will get this I5 related term. So, all these other currents are 0, and here also it is 0, and then here we are getting 1. And then if you see this equation number 5, so I36 which is equal to I6. So, here 0, 0, 0, 0, you are getting 1 here, and here we are getting multiplied by -1. And last equation, that is equation number 6, we are getting all the entries 0 except I56. So, we are getting 1 here. So, on the last column we are getting 4 entries which are 1, and again I am calling this matrix as BIBC matrix, which basically converts your bus injection to branch current matrix. Now, if you observe here, this particular current, which is represent basically loop current, which otherwise if this loop current is not there, actual system is radial one. So, if you remove this branch, system becomes radial. That is why this added branch, which is basically making loop, I can consider I loop. So, these are actually branch currents, and this extra branch which is added basically making loop, I am calling it as I loop. So, basically I can write this I branch currents and then I loop current. So, I loop current is only this I56. If there are 2 loops, there will be 2 entries in I loop. If there are n or you can say L loops, there will be n entries in I loop, and then there is this BI BC matrix, and here these currents are basically nodal load currents. So, I can say I node, and then there is one entry which is similar to your left hand side, which is again I am calling it as I loop. So, we have got this equation, say equation I here, which we will be using it later. So, we have got BIBC matrix for weakly mesh system. Let us see how we can get BCB matrix for weakly mesh system. So, to get the BCB matrix, we need to write the KVL equations of the voltage nodes. So, we know that V2 will be equal to V1 minus Z12 into I12, basically this node voltage. V3 will be equal to V2 minus Z23 into I23. So, V2 already calculated. So, the same thing I can write, it will be equal to V1 minus Z12 into I12 minus Z23 into I23. Similarly, your V4 will be equal to V3 minus Z34 into I34. So, it will be V3 we already got it here. So, it will be V1 minus Z12 I12 minus Z23 I23 minus Z34 into I34, and then V5 will be equal to V4 minus Z45 into I45. So, V4 we already got it here. So, it will be V1 minus Z12 I12 minus Z23 I23 minus Z34 I34 minus Z45 I45. Then only node 6 is remaining. So, V6 will be equal to, now this V6 which is connected to node number 3, because we are considering this as a radial branch, this as a loop branch. So, we will consider only radial branches. So, here it is connected to node number 3. So, it will be V3 minus Z36 into I36. V3 we have got it here, which is V1 minus Z12 into I12 minus Z23 into I23 minus Z36 into I36. And then one more equation I am writing considering this loop here. So, if you consider this loop starting from say 3, 4, so we know that if you apply KVL for this particular loop, total voltage of the loop will be equal to 0. In that case, this drop, which is basically Z34 into I34, then this drop will be plus, if you see the current direction, Z45 into I45. Then this drop, by considering this loop branch here, which is again plus because you are in same direction of loop. So, it will be Z56 into I56, and then last is this branch. However, you can see that the current direction is in opposite. So, here we need to put minus sign, Z36 into I36. So, basically we applied KVL for this loop, and let us say this is your equation number 1, equation number 2, equation number 3, equation number 4, 5 and 6. And if you put them into matrix format, we have seen that the matrix is something like this. Here we know that this is nothing but V1 minus V2, V1 minus, so V1 actually voltage at this node, V1 minus V3, V1 minus V4, V1 minus V5, V1 minus V6, and here we are getting 0 for the last equation. So, there are actually voltages in first 5 equations, and last equation there is no term which is related to voltage. So, that is why we put 0 here, and right hand side we are considering this impedance multiplied by current. So, these currents are I12, I23, I34, I45, I36 and I56. So, if you see equation number 1, there is only one Z12 which is getting multiplied by I12. So, here only Z12 is present which is getting multiplied by I12. So, all other entries are actually 0. Equation number 2, if you see, there are Z12 multiplied by I12 and Z23. So, here we are having Z12 and Z23, other entries are 0. Equation number 3, we are having 3 entries, those are Z12, Z23 and Z34, and all other entries are 0. Equation number 4, Z12, Z23, Z34 and Z45. So, Z12, Z23, Z34 and Z45, other entries are 0. And here we are having Z12, Z23 and directly Z36. So, Z12, Z23 and this is 0 0, and here we are having Z36 and 0. And last equation, if you see, we are having Z34, Z45. So, here Z12 this is not there, Z34 we are having, Z45 we are having and Z56 we are having. So, here there is Z56 is coming, and I36 is getting multiplied with respect to minus Z36. So, if you write this equation into matrix form, we are getting this equation here, and this we call it BC BV matrix, basically branch current to bus voltages. However, it is not exactly the voltage here. So, we can write this collectively here. So, up to this term I am calling delta V, which are voltage difference, and this I am calling matrix of zeros. So, depending upon number of loops in your system, the size will be decided. So, if there are L number of loop, there will be L number of rows of 0 voltage into your matrix system. So, here I can just write this, it will be delta V and then 0 will be equal to your this BC BV matrix multiplied by, again if you see up to this, up to I36 from I12, we are having I branch, because these branches are basically radial branches, and then I56 which is basically making loop. So, that current I am writing as a loop current. So, depending upon number of loop forming branches, this loop current entries will be decided. So, I divided this into 2. So, let us say this is equation number II. So, equation number this 1 and 2 I can just take on this slide. So, first equation which we had got is I branch equal and then I loop, which is equal to your BI BC matrix, and this is equal to your current I node, and then this is again it was I loop, and then this was your for equation number 1 we had got, and then we had got delta V 0 which is equal to your BC BV matrix, and this is getting multiplied by I branch and I loop here, which is your equation number 2. And what I can do, actually I can just put this equation into the here. So, it will basically become your delta V 0 will be equal to BC BV matrix multiplied by your BI BC matrix multiplied by your I node minus this I loop here. So now you can see that in this case this I node currents are actually known because we can calculate them from the loads which are connected at each node. However, this I loop currents are unknown, so we need to eliminate them. So to do that, let us see this multiplication if you do, that is BCB multiplied by BIBC. So it will be delta V 0, and let us say this matrix is having 4 terms A, B, C and D. After making the multiplication, multiplied by I node and I loop. Now the size of this matrix will be m by m. If there are m number of branches, if there are n number of branches in the system, size of this matrix will be m by m number of branches, consisting loop branches also, excluding radial branches plus loop branches. If you consider both, if there are m number of branches, then the size of this will be m by m. Out of this, your size of A matrix will be n minus 1 by n minus 1, where we know that n is actually number of nodes in the system. So n minus 1 by n minus 1, which will be size of A matrix. Size of B matrix will be, there will be n minus 1 rows and there will be L number of loops, say L number of loops are there, then size will be L columns will be there in B matrix. In C matrix there will be L rows multiplied by your n minus 1 columns, and D matrix will be L by L, where L is actually loop forming branches and capital M is, I am considering total branches including radial plus loop. Now if you see this equation here, and as I told you, these loop currents are unknown and we want to eliminate them, what we can do, this equation I can write into 2 equations. So delta V will be equal to A into your I node plus B into I loop, and second equation 0 will be equal to C into I node plus your D matrix into I loop. This is your D matrix, and from this equation I can just write your I loop will be equal to minus D inverse into C into I node, and this equation I can put into this equation, means instead of I loop I can replace it by minus D inverse C. So I can write this equation delta V. So delta V now will be equal to A into your I node plus, or here it will be minus, because that minus sign is coming from this equation here. So it will be minus B into D inverse into C I node. So this I can write by taking I node common out. So A minus B into D inverse of C into your I node. So now we have got this matrix here, which will become your new DLF matrix, distribution load flow matrix, similar to your radial system. So for weekly system, weekly mesh system, your DLF matrix will be equal to A minus B into D inverse C. And your algorithm will remain same, exactly same as we are using radial system. Only what you have to do whenever there are weakly mesh system, you have to get the DLF matrix using this particular equation here, and once you get the DLF matrix for weakly mesh system, exactly same algorithm which you have developed for radial system can be used. Now, to understand this process, let us take one example, or before going to the example, let us say how we can calculate this modified BIBC and modified BCB matrices directly. Okay. So, let us see, consider this example again, and when this system was radial, we already considered it, and when this branch was not there, and when we had got your BIBC matrix earlier, that BIBC matrix was whatever I have shown it here, and we had got this matrix here. So, these are basically we seen that we give node number here 2, 3, 4, 5, 6, and here we give your branch numbers, that is 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 3 to 6. These are basically radial branch numbers. So, we already seen that how to get this particular BIBC matrix, and we have already seen the algorithm, and this example also we have seen. Now, let us see when we have added this branch here, and which is basically making it weakly mesh system, and this branch is basically 5-6 branch, and we have seen that earlier when we have written. So, this 5-6 branch I am writing it here, and as I told you, 6 equation which you added earlier is involving only loop branch current, means just I have written 6th equation. When we have formed BIBC, I had written I56 is equal to I56. So, if there are many number of loops, say one more loop add between say 3 and 5, then one more equation which we will adding, that is I35 is equal to I35. So, here all these entries will basically will be 0 only. So, in earlier equation there is no term which is related to I56. So, I will just erase this. Now, when I am adding the branch which is basically I56, this one, what we need to do, we have to subtract your column 6 from column 5. If you are considering direction of this current in this branch is from 5 to 6. So, subtract 6 from 5. If you are considering in opposite direction, subtract 5 from 6. Okay. So, in this case we are considering current is starting from 5 and then ending with 6. So, we need to subtract this column 6 from 5. So, in this case this 1 minus 1 it will be 0, here also 1 minus 1 it will be 0, here it is 1 minus 0, so it should be 1 here, 1 minus 0 it should be 1 here, and here 0 minus 1, so it will be minus 1 here, and as I told you we are considering this equation, that is I56 is equal to I56, that is why we will get 1 here. So, you can see that once you form your radial BIBC matrix, you can immediately convert into weakly meshed BIBC matrix just by knowing which branches are making the loops. So, if you know that, you can easily find your BIBC matrix here by using the algorithm which I just explained it here. So, as I told you, whenever we are considering branch from 5 to 6, subtract 6 from 5th node. In BCB also we can use same philosophy. So, we have seen that here we give node numbers. So, 3, 4, 5 and then 6, and here we give branch numbers. So, it is 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 3 to 6, and this is corresponding to 5 to 6. And we have seen when we have wrote the equations for forming the BCB matrix in this. So, in first 5 equations we are not getting any term related to I 5 6. So, here in any of the equation we are not getting any term which is related to 5 6. So, basically in first equations we are not getting any term which is related to 5 6. So, we need to put 0 there. So, we need to add one column which is basically 0 0 0 at 5 6 line. And then similar, since I am adding branch from 5 to 6, direction of current is from 5 to 6, then you need to subtract 6th row from 5th row. So, in this case it will be Z12 minus Z12, it will be 0, Z23 minus Z23 0, it will be Z34 minus 0. So, Z34, Z45 minus 0, Z45, 0 minus Z36, it will be minus Z36. And here, as I told you, in second step you need to replace this entry by impedance of Z56. So, here we need to put impedance of Z56. So, you can see that by using this logic here you can add many more branches into your system, which makes your system weakly meshed. So, we have got this BIBC and BCBV matrix, and we have seen the algorithm also how we can modify your radial BIBC and radial BCBV matrices, so that we can get it for weakly meshed system depending upon which lines are making loops. Let us take one example which illustrate this process here. We already seen it, just I will show you how we process it here. So, as I told you in the same example, so we had used data till this point. I added one more line which is from 5 to 6 having impedance given in this column, okay, and then loads at each node already considered. So, there will not be entries here. So, this is your line data of weakly meshed system, and this is your node data or bus data of weakly meshed system, and using these columns we form your BIBC and BCB matrices. As I told you, first open the loop forming branches. You can open any branch. If this loop is getting formed here, you can open this branch or this branch or this branch, any branch can be opened, and that will be considered as I loop branch. And first find BIBC and BCB matrices for radial system, and then modify these matrices including each of the loop forming branch. So, if you do that, you will get BIBC matrix. We have seen already how we got it, and then BCB matrix also we have seen which you have got. Here I just put the impedance, actual impedance values. So, this is your BCBV matrix, and then we have seen we multiply them. So, BCBV multiply by your BIBC matrix, and that we have seen that we get that A, B, C, D matrix, which I explained in weakly meshed algorithm system, where A we have seen n minus 1 by n minus 1. Here number of nodes are 6. So, size of A will be actually phi by phi, n minus 1 by n minus 1, because your n is actually equal to 6, total number of nodes are 6. So, here so this will form your A matrix, this will form your B matrix, this will form your C matrix, and this will form your D matrix. So, if there are actually number of loops are more, there will be more number of rows in C matrix. Similarly, there will be more number of columns in B matrix, and D will be depending upon number of loop multiplied by number of loops. So, it will be L by L size. Since in this case only one loop forming batch we are considering, the size of D is 1 by 1. And then we have seen that the distribution load flow matrix DLF we have got, which is equal to A minus your B into D inverse into C. And if you do that, this operation, we have seen that the size of this DLF matrix is basically n minus 1 multiplied by n minus 1. So, it will be n minus 1 by n minus 1 size of this DLF matrix. So, from this, if we get this DLF matrix by doing A minus B into D inverse C, you have got this DLF matrix for that same system. And once you get DLF matrix, your algorithm will be same, exactly same algorithm you can use. That is basically first calculate your nodal current using this equation divided by Vj, which is calculated at earlier iteration, take star of it. So, it is equation number 1. Equation number 2, so it will give you I node matrix, which is basically I2, I3 up to In, and then we get delta V, which is basically DLF matrix which you have formed in last slide, multiply by your I node matrix, and this is your equation number 2. And the third equation is Vj at kth iteration will be equal to Vs minus delta Vj at any kth iteration. So, here we are getting at kth iteration using nodes I node current at kth iteration. And then as explained in case of direct approach based method, the process will get repeated, that is first get nodal values of current. In first iteration we calculated this nodal value load currents by using voltage which is equal to 11 kV at each of the node. So, Vs is 11 kV, then using equation number 2 get delta V, then using equation number 3 update the voltages, then compare with voltages with earlier iteration, get the error, go to next iteration, again calculate current, delta V, update the voltages, get the error, and keep on repeating till we actually converge to result where error between voltages of this iteration and earlier iteration are negligibly small, or you can say below the tolerance value. In this case we have considered tolerance value which is 1 into 10 raised to minus 5. If you are keeping lower tolerance value, it will take more iteration. If you are keeping less tolerance value, it will converge in few iterations. So, here for this particular tolerance value, the algorithm has converged in 8 iteration. So, in today's lecture, we have seen how we can get or how we can consider a weakly mesh system to solve the load flow problem, because till now before this lecture whatever systems we are considered were radial, and in this case first we have seen how we can consider this loop forming branches and how to get BIBC and BCB matrix. And then we have seen if you are already the BIBC and BCB matrix for a radial system, how we can modify these BIBC and BCB matrices to include loop forming branches. So, that modification or simple algorithm I explained you, and once you get this modified BIBC and BCB matrix, you can get modified distribution load flow matrix by dividing the multiplication of BCB and BIBC into 4 parts, and once you get that DLF matrix, your algorithm will be same as earlier which is used for radial distribution system. So, here we complete the direct approach based method, and I have considered one example also which illustrate how we can use this direct approach based method for weakly mesh system. So, next time we will see one more algorithm which is based on implicit Z bus matrix. Thank you.